This lecture is on Chapter 7.4 on precipitation reactions and solubility rules. So recall our precipitation reaction, which are processes in which soluble ionic reactants yield insoluble solid products that fall out of solution. And so again, we have two different aqueous salts combining together to form at least one solid compound, a solid insoluble salt, and then either an aqueous or a solid second salt. And this follows a double displacement reaction or a double replacement reaction where the cation and anions of our soluble reactant salts switch partners. And so this is classified as a double displacement reaction. So how can we predict which compounds are going to form together to form an insoluble product and which combinations of cations and anions will be insoluble and which will be soluble? And so this introduces a term called solubility, which is the extent to which a compound will dissolve in a given amount of solvent at a given temperature. Okay, so solutions or salt combinations that form a solid are insoluble. Ionic salts that dissolve in solution are called soluble. So we have a few rules set out that allows us to predict whether a certain compound will either be soluble or insoluble. And so these rules you just sort of have to memorize. So I suggest as we're going through these rules to pull out a periodic table and actually look at the position on the periodic table as we're going through these specific rules. And that will help you to sort of visualize these rules. That'll help you sort of memorize them. All right, first rule. A compound is soluble if it consists of one of the following cations. The group 1A cation, so the alkali metals, so lithium all the way down through cesium. Any salt that contains an alkali metal will always be soluble, no exceptions. Any salt that contains the ammonium cation will always be soluble, with no exceptions. So that NH4 polyatomic cation will always be soluble. Two, a compound is soluble if it contains one of the following anions. If it contains nitrate, perchlorate, or acetate, it will always be soluble, with no exceptions. All right, so nitrate, perchlorate, and acetate are always soluble. Okay, salts that include halides, so halogens are group 7A or group 17. We're going to see that those will always be soluble, except we have a few exceptions. If they mix together with silver, mercury, or lead. So again, take a look at your periodic table and think about your halogens here, all the way in the far right, are always soluble unless they contain silver, mercury, or lead. Next is sulfates. Sulfates will always be soluble except if they are with strontium, barium, mercury, or lead. Okay, so strontium and barium are in the alkaline earth metals, and then we have mercury and lead, the same two that are in with our halides. Okay, so memorize those. Rule 3, a compound is insoluble if it contains one of the following anions. All right, so this is insoluble, meaning that it will form a solid. So if you have a carbonate or a phosphate, you will always be insoluble, except obviously if you're mixing with our alkali metals, our group 1A, and our ammonium ions, which we previously stated are always soluble with no exceptions. Next are hydroxides, sulfides, which are S2 minus, and oxides are always insoluble, except again if they're with our alkali metals or ammonium, because we know that they are always soluble with no exceptions, or with calcium, strontium, or barium, which is our heavier alkaline earth metals. Okay, so again, I recommend when you study this to actually look at the periodic table and kind of memorize visually where those exceptions occur on our periodic table. And so here's a table that reviews those solubility rules we just went through. And so I'd like to point out a few features that can help you sort of conceptualize these solubility rules of why certain ones are more likely to be soluble and certain combinations are more likely to be insoluble. Okay, so if we take a look at them, most soluble ions are singly charged. So they either have a 1 plus or a 2 plus charge. Again, this is just a sort of a trend. It's not a firm rule. It's just saying a general trend. Okay, so if we take a look, all of these alkali metals, the group 1A, are all plus one charge. Our ammonium ion is a 1 plus charge as well. Our our halides are 1 minus charges, nitrate 1 minus. Okay, so all of the perchlorate acetate, those are all 1 minus charges. So these singly charged tend to be these soluble compounds. Of course, there are some exceptions here. We have sulfate, but that's sort of a good way to sort of think of it. And so, whereas our insoluble compounds, we can see a lot of them are higher charges: carbonate, sulfide, and phosphate. Hydroxide is singly charged, but that's sort of an exception. So we can think of so if we're actually thinking through intellectually why solubility, um, what actually is happening when we dissolve an ionic substance. So let's go up to the board and think about the process of solubility. So we're dealing with an ionic salt. And so we know that ionic salts orient themselves in a crystal lattice. Okay, and so we have this cube sort of shaped crystal lattice, right? And so this crystal lattice we know is held together based on Coulomb's law, where we have our lattice energy is proportional to the charge on our anion, the charge on our cation over the interatomic distance squared. Okay, and so this lattice energy is the energy that keeps this salt held together. Okay, and so the higher the charge, or the smaller the interatomic distance, yields to a higher lattice energy. Okay, and so when we're dissolving these crystal lattices, that means that we're going to break apart all of these ions in solution. So the process of dissolving these ions, so the positive and negative charge ions here, in order for us to dissolve these guys, we need to have our solvent come and interact with each of these ions and rip them apart. So what we would have here would be our water. So water being a polar molecule with a partial negative and a partial positive dipole moment, we're going to have an interaction with the negative portion of water, ripping away these positively charged ions. And we have other ions where our positive, or so we have our other water with the positive pole ripping away the negative ions. And so these are going to be our ion dipole interactions between the water and the salt itself. So the strength of these intermolecular forces, of the ion dipole interaction between our solvent and the ions in the crystal lattice, has to be stronger than the lattice energy that holds the salt together in order for it to dissolve. So again, the intermolecular forces between the solvent and the solute, the intermolecular force ripping it away, has to be stronger than the lattice energy holding it together in order to dissolve. So the higher the lattice energy that you have, the more tightly this crystal lattice is held together, and the less likely it is for these ion dipole intermolecular forces to be strong enough to rip it away. So if we take a look at our insoluble species, those are ones that have large charges. And also those are compounds that have smaller interatomic distance as well. Okay, so let's now, based on these solubility rules, let's predict whether each of the following compounds are likely to be soluble in water. So I'd pause the video and try to start to go through some of these on your own. Okay, so our first one here, cadmium carbonate. So we expect this to be insoluble because it has a carbonate, and the carbonate does not include one of our exceptions. Next, magnesium oxide. This one is also expected to be insoluble because we have our oxide, which are considered to be insoluble, and magnesium is not one of our exceptions. Next is sodium sulfide. We expect this to be soluble. Even though sulfides we expect to be insoluble, this sodium is an alkali metal. So therefore, all alkali metals are soluble. Next, lead sulfate. So lead sulfate is insoluble. Even though sulfates tend to be soluble, lead 2 is one of the exceptions to that rule. Next, ammonium phosphate. We expect that to be soluble because all ammonium salts are soluble. Next is mercury chloride. This is insoluble because even though our halides are expected to be soluble, mercury is one of the exceptions. Next, which of the following pairs of solutions when mixed will form a precipitate through a double displacement reaction? So take a minute to work through that. Okay, so the correct answer here is C. So let's take a look and go through and identify the possible answers for each one and determine why the correct answer is indeed C. So if we take a look at our first mixture, sodium chloride and potassium nitrate, we switched their cation and anion partners. So that's going to have sodium nitrate, NaNO3, and then we'll have potassium chloride. Okay, and so we know that any alkali metal, group 1A metal, is going to be soluble. So we know this has to be aqueous to start with. Second is going to be the same idea. K plus is an alkali metal. So we again have aqueous. Next, ammonium bromide plus calcium sulfate. Okay, so we'll switch partners here. We'll have ammonium 2 sulfate plus our calcium bromide. Okay, so we take a look here and we see that any compound that includes ammonium is going to be soluble, so that has to be aqueous. And so for our halogens, we know that all of our halogens, Br, are going to be soluble unless they have our exceptions of our silver, our mercury, and our lead. Okay, so since that doesn't include, that gives us our aqueous. Next, magnesium chloride plus sodium hydroxide. Okay, switch our cation and anion pairs. We have magnesium hydroxide plus our sodium chloride. NaCl. And then, so if we wanted to balance this equation here, we would have a 2 and a 2, but balancing the equation doesn't specifically matter. All right, so now we take a look at our solubility rules here. We know that all hydroxides are insoluble unless they are mixed with our alkali metals, our group 1A, ammonium, or our larger alkaline earth metals that are calcium, strontium, and barium. And so since this is magnesium hydroxide, we know that's going to be solid, insoluble. Sodium chloride is going to be aqueous. Next, silver nitrate So that tells us that C is going to be our correct answer. Silver nitrate plus lithium perchlorate. All right, so that gives us our silver perchlorate plus our lithium nitrate. Okay, so we know that all perchlorates are soluble with no exceptions, so that gives us aqueous. And we know that all alkali metals and all nitrates are also soluble, so those are both aqueous. Finally, we have magnesium bromide plus our aluminum chloride. Okay, so we have magnesium chloride, MgCl2, plus our aluminum bromide. Okay, so if we wanted to balance this equation here, we would have, so we need to have 3, 2, 2, and 3. Okay, to balance that equation. All right, so we take a look at magnesium chloride. So we know that chlorides are all, chloride is a halide. Those are all soluble unless you're mixing with our silver, mercury, or lead. So therefore, that has to be aqueous. And again, bromine being a halide are all soluble unless they're mixed with silver, mercury, or lead, which means that that also is going to be aqueous. So that shows us very clearly that our only answer that has an insoluble product would be answer C. All right, next. Write the molecular ionic and net ionic equations for the reaction that occurs when aqueous solutions of silver nitrate and sodium carbonate are mixed. So take a moment to work through that on your own. Okay, so we have silver nitrate, aqueous, plus sodium carbonate are going to form switching partners, are silver carbonate plus sodium nitrate. To balance our equation here, we have to have 2, 2. All right, that gives us 2 silvers on each side, 2 nitrates on each side, 1 carbonate on each side, 2 sodiums on each side. All right, and then so identifying our soluble and insoluble species, we know that carbonates are always insoluble unless they're combined with our alkali metals or our ammonium. So we know that this is going to be a solid. And sodium nitrate we know is going to be fully aqueous. Okay, so this balanced equation here is our answer for the molecular equation. Next, our total ionic equation would be split apart 2 Ag plus aqueous plus 2 nitrate aqueous plus 2 sodium aqueous plus carbonate aqueous, yielding we keep our solid species together, Ag2CO3 solid plus 2 Na plus aqueous plus 2 NO3 minus aqueous. All right, so that's our answer for our total ionic equation. And then finally, our net ionic equation, we identify our spectator ions, which are going to be our nitrate and our sodium. Sodium and nitrate are present on both sides, so we can cut those out, meaning that we have 2 Ag plus aqueous plus CO3 2 minus carbonate gives us our insoluble silver carbonate solid for our net ionic equation. All right, so with that, we are finished for the day. Thank you.